Hi everyone, good morning, good afternoon, good evening, depending on where you're joining us from. It's my pleasure to be back again, this time bringing you a closer look at Kubernetes. So even if even if you have not attended any of the previous sessions, and this is the first webinar you're attending in this series, you can still follow through because every session is completely independent and it covers a specific topic. So this series is all about deploying and managing containerized workloads in the cloud. And as Karan mentioned, in the last 3 sessions, we covered the essentials of Docker, containers, and an overview of Kubernetes deployment. This session is going to be interesting where I'm going to take a closer look at Kubernetes and introduce the primitives of Kubernetes. So this session assumes that you have access to a live Kubernetes cluster, ideally running it on DigitalOcean based on stack point, where I demonstrated it last time. But any Kubernetes installation is fine, including what is called as Minikube. But my suggestion is go through the previous webinar where we set up a multi-node cluster on DigitalOcean with just a few clicks. StackPoint is making it very easy. So my suggestion is to go back and look at the previous session to get started with Kubernetes setup. So with that, I want to do a quick a recap of the Kubernetes architecture and then walk you through a set of primitives like namespaces, nodes, pods, and so on. The objective of this webinar is to get you very familiar with the Kubernetes terminology, the nomenclature, and the way of packaging and deploying applications in this environment. So let's get started. This is a quick recap. I'm sure if you have attended my previous session, you can relate to it. If you haven't, let me do a quick recap of the architecture. Essentially, Kubernetes is like any other distributed computing environment. It has a master and a set of worker nodes. The master node is responsible for managing the entire cluster. It essentially has 3 parts. One is called the API server, which is obviously exposing the API through which the clients will interact with the cluster. It also has a controller whose job is to manage the entire cluster. It also has a scheduler which will take care of positioning and placing the containers that you are deploying in the cluster. So that is the role of the master. The actual workloads, which are nothing but containers packaged for Kubernetes, will be running in one of the worker nodes. The master is not responsible for physically hosting your application. Instead, it delegates the application to one of the nodes, unless you explicitly want the master to be yet another node. But in majority of the cases, the master's responsibility is to own and manage the cluster than running the applications. The core job of nodes is to host your applications, and they are the workhorses of the cluster. So there could be multiple nodes, and these nodes have access to a registry. It could be the public Docker hub, or it could be a private registry, but your cluster should be able to talk to a registry where the images are stored. So once you have this setup in place, you will use either the user interface, which is the Kubernetes dashboard, or the CLI. I choose CLI because it gives you a lot of control and you can automate a lot of things. So using one of those interfaces, you will submit jobs to Kubernetes master, which will be delegated to one of the nodes. So that is a quick 2-minute recap of the Kubernetes architecture. I covered this in detail in the previous session. So it's time for me to take you to the next level by introducing the primitives and the building blocks of Kubernetes. So it's very important for us to understand what is a cluster, what are the nodes and namespaces, because we'll frequently use this terminology. Cluster is basically a representation of a Kubernetes deployment. So if you have rolled out Kubernetes in your environment, either in your data center or in the cloud, it typically results in one cluster per installation. In many cases, customers run multiple clusters, but that is only meant for pretty massive, pretty large deployments. In majority of the cases, even if you are using something like StackPoint targeting DigitalOcean, you will typically end up creating one cluster per installation. So once you have a cluster, which represents one Kubernetes deployment, you need to understand nodes. Nodes are, as I mentioned, are basically the workhorses. They could be physical or virtual machines. In our case, we are actually dealing with DigitalOcean droplets, which are VMs that are running the nodes. So once you have the nodes set up and the cluster up and running, then you need to get familiar with namespaces. So a namespace is essentially a logical boundary for applications deployed within the cluster. For example, if a large organization has set up a Kubernetes cluster, it could logically partition the cluster into multiple namespaces. For example, one for finance, one for HR, one for sales, one for IT. And each namespace is responsible for running one logical set of applications. So in another scenario, an organization might define dev, test, staging, and production namespaces. It gives you some kind of an isolation, and namespaces make it easy for you to manage the application so that there is no overlap. And Kubernetes also enforces certain policies and restrictions when you want to talk to applications running in another namespace. So it acts as the basic boundary between applications, and applications are expected to be deployed or launched in one of the available namespaces. By default, when you set up a Kubernetes cluster, you get a couple of namespaces. The first one is the kube system namespace, which is reserved for running Kubernetes system components. You never have to meddle with it. It also comes with another namespace called default, which is what is used for deploying our application. So if you don't mention any namespace, it will automatically get placed in the default namespace. So this depiction here that you see on the screen represents what we have talked about. So there is a master node, then there are multiple worker nodes, and all of them are currently responsible for a Kubernetes cluster. And within the cluster, you have these dotted lines with these boxes, and they represent namespaces. You can have multiple namespaces. All right. Once we understand these concepts, then we get to deal with the fundamental deployment unit of Kubernetes, which is called as a pod. So what is a pod, and why is it so special? Aren't we already dealing with containers? Why can't we directly take a Docker container and run it in Kubernetes? So Kubernetes brings another level of abstraction to containers. And that's because in many cases, applications need to have more than one container. One classic example is, if you're familiar with web scale applications, every web server typically talks to a cache, a Redis or a Memcache instance. It could be used for session management. It could be used for caching frequently accessed data. Let's say we have coupled the web server with a cache server where we are caching the most frequently accessed data from the database so that we can avoid a round trip to the expensive database. So when you're actually deploying an application, you need to make sure that every web server has a cache attached to it. Now, when you're deploying containers and scaling them, it becomes a little bit tricky to make sure that every time a web server is scaled, you also need to scale the corresponding cache container and place it along with the web server. So technically speaking, this pair of containers, one is web server, one is a cache server, they need to be packaged and treated like one logical unit. And that's exactly what pod is all about. It's a group of containers that are always co-located and co-scheduled. Similarly, let's say you have a logging agent, something like a New Relic, and an application is writing the logs or calling an endpoint within this container, and it is streaming the logs to a central endpoint, which could be on-prem, which could be something like New Relic. So how do you ensure that every container is associated with another agent responsible for logging? Again, you need to package these containers as a pod. There is no hard and fast rule that you need to have more than one container in a pod, but ideally pod contains at least one container, but it can go beyond that. So basically, a logical collection of containers are always packaged as a pod. And the best thing about this approach is all the containers that belong to the same pod share the same operating system context. What it means is they all get the same IP address. If you get into one of the containers running inside a pod, you'll notice that it shares the same IP address as rest of the containers. And every port that is open in the pod is available to the container running inside the pod. They all share the same host name. And if you attach a volume, which we'll explore in the upcoming sessions, that volume as storage endpoint also becomes available to all the containers. So the idea is to reduce the communication overhead between containers that need to run as a group. So the communication between containers running in the same pod uses IPC, interprocess communication, instead of RPC, which is very expensive. So when Kubernetes was designed, they took a very conscious decision of packaging containers as pods, because it gives you additional flexibility and gives you a lot of other possibilities of creating a very declarative and creating a very logical unit of deployment. So pods are scheduled in one or more nodes. So when you create a pod and submit that to Kubernetes, it is going to be scheduled in one of the available nodes. So you take a container, you package that as a pod, and you submit the pod definition to the master, and the master will place the pod in one of the available nodes. So that is the workflow involved in it. So essentially, pod is nothing but a thin wrapper on top of an existing container. So it is not very different, but it gives you a lot of flexibility and sometimes additional capabilities to deal with multiple containers that need to go along. But if you're wondering if you can package a database container and a web server container, that's a bad idea. The reason is, when you scale your pods, the container that belongs to the pod will also get scaled, which means the database will also get scaled, and then all the instances of the database would be out of sync. So ideally, pods that are clubbed together, containers that are clubbed together as a pod should be ideally stateless, and they shouldn't really have dependencies on other containers or other pods running in the cluster. So combining a stateful pod with a stateless pod is not a good idea. So never attempt to package your web server and database server together as a pod. That's highly discouraged, and that is not the use case. But if you have stateless containers and they need to go together, then they can be packaged as a pod. So this is a visual representation. The reason why I built this is pod 1 contains 3 containers and it is still one pod. Pod 2 contains only 1 container and it is still a pod. So essentially, a pod is basically a collection of one or more containers that need to coexist and that need to be co-located. So that is the definition of a pod. So nothing like showing you how to create a pod and what are the differences between a container and a pod. So let's explore nodes, let's explore namespaces, and we'll also create our very first pod. So time for me to jump to the demo. All right, so a bit of context here. So I'm using StackPoint and it has set up a 3-node Kubernetes cluster in DigitalOcean. It's currently running in Bangalore. This is my master. These are 2 worker nodes. So with this in place, let's switch to the command line. And when you type kubectl get node. So kubectl, as I introduced in the last session, is the command line interface to talk to the Kubernetes cluster. So now I set this up today morning. That's why you'll actually see that the age of this cluster is roughly about 8 hours. So we have 1 master node and 2 worker nodes. Similarly, you can also explore the namespaces. So when you type kubectl get namespaces, it actually shows multiple namespaces. StackPoint system is used by StackPoint to maintain its own components, so this is not visible. Kube system is another internal namespace. Kube public is another internal namespace, but default is what we'll end up dealing with. So if you don't mention any namespace explicitly, it actually goes into the default. You can also very easily create a namespace. So you can type kubectl create namespace followed by, let's say, Sammy, right? So I want to create a new namespace and it immediately becomes available. So now Sammy is a new namespace. And when you're deploying custom applications, you can mention this as the namespace and all the pods and all the logical components that belong to this will go into it. So that's how you basically deal with namespaces. All right, how about a pod? Right, if you remember last time I walked you through a command which was called kubectl run, and that was a very high level overview of running containers in Kubernetes. I was just scratching the surface, but serious applications are always declared and written as YAML files before they get deployed. So how does the pod look like? Well, this is actually the pod, right? And this pod, if you look at this file, it is basically a YAML file, yet another markup language. And after dealing with INI files and XML, JSON, currently the most popular markup to define the declarative language, for infrastructure, is basically a YAML file. So we have this YAML file, and it starts with an API version, because Kubernetes has multiple versions of APIs. You need to mention which API you are targeting. And then Kubernetes has multiple objects. Pod is just one of them. So you define the kind of object in Kubernetes you are dealing with is pod. Then there is some metadata, which is self-explanatory. This is where you will give a name to your pod. We are calling this as web pod. And it also has a couple of labels. There is a lot of significance attached to these labels. We'll come back to it in a minute. But for now, this is an arbitrary set of key value pairs that we attach to the pod. At this point, it doesn't really have any significance, but later on, this becomes very important. So metadata section will have the name of the pod, and then there are labels. Now, don't get confused between the name within labels and the name here. This is the object name for pod, and this is an arbitrary name that I'm giving. It can be completely different, and it could be anything else. For example, I could very easily define this as an ID. It doesn't matter. So, so we have this, and then there is the spec. So a spec section contains the definitions of the container. So you can have, it's an array. As you notice, there is a hyphen which represents an array. So I can actually have multiple containers under spec. But because this is our first pod, I kept it very simple with just one container. So I'm creating a container with name myweb, and the Docker image for this is Nginx, right? For example, if I give this, it will become more clear. So when we actually give a tag, basically Kubernetes will pull one of the images from the registry. If you have a private registry, you could mention that here. For example, if I'm using Google's container registry, I would actually say gcr.io/, and then Kubernetes will try to grab the image from your custom registry. But if you don't mention any moniker in front of the image, it by default pulls it from Docker Hub. Now we are running Nginx, and it is a web server. So obviously we need to expose a port. So that is the next thing. So we are now exposing a container port, which is TCP/IP based, and we also gave it a name. This name is arbitrary. You can actually give anything, but a name given to the port will help you discover them at a later point. So it's a good idea to name your ports, because later on when you want to talk to any of the pods that match a specific label, and you want to talk to one of the ports, you can even use the name. It's not always the port number. So you can explore further on the Kubernetes documentation section, but all I want to highlight is you can actually give a name to the port, and there's a lot of importance and significance to it. All right, so in a lot of sense, this is not very different from a Docker run command. So if you remember, when we played with Docker, we used this command called docker run --name is equal to myweb, and then -p 80:80, and --host name was whatever, like myweb, and that's when you basically hit enter, and Docker will translate that command into a running container. Now this YAML file is not very different from the Docker run command, except that it is more verbose and more declarative. And there is a lot of advantages. There are a lot of advantages in using a declarative file. You can version control this. You can actually put this on GitHub and every time you modify, you can commit, you can roll back. So having a declarative mechanism to define your stack is always preferred, because you can always version control, roll back, and treat it like your code. That's why it is called infrastructure as code. So it joins the application repo, and you can treat it as yet another artifact. So this might look slightly more verbose, more a lot of text and a lot of elaborate definitions, but it all makes sense when you are using DevOps, when you are using CI/CD, and when you are using versioning. So that is the pod, object pod. So basically in Kubernetes, every object that we submit belongs to some type, and that is what is mentioned here as kind. So everything is an API object. So let's go ahead and check what pods we have in the cluster. As we notice, there are no pods, no resources found. So it's time for us to create our first pod. How do we do that? kubectl create from file simple pod.yaml. Now this is going to create a pod for us called web pod. And where does this web pod come from? Well, that is the name of the pod. Whatever you put here will be used to identify your resource. Now when we run kubectl get pods, you'll notice that web pod is getting created, and in just a few seconds it should move to the running state. Excellent. You can also use a command called kubectl describe pod followed by the name. Now this is more elaborate and gives you a lot of insight into what really happened. So it tells you these are the labels attached. Now this is the IP address that the pod got. Remember, a pod is like a mini unit. It gets an IP address, not routable, but it is available within the cluster. It also tells you the state. It tells you the timestamp when it got started. If there are any volumes attached, it shows up here. So kubectl describe is a pretty powerful command. You can actually see a lot of information. So it got scheduled on worker 2. That means our pod is now running in worker 2 node. It started pulling, then it got pulled, then it got created, and finally it got started. So that is how we create the pod. But I know you are eager to access the pod and actually look at the web server, right? But unfortunately, a pod in itself cannot be accessed directly, because a pod is running inside the Kubernetes cluster. Unless you are in one of the pods or one of the nodes, you may not even reach the pod. And there is a reason why it is designed like that. So a pod is now successfully created, and it is available on port 80, but on a specific IP address that is confined to the cluster, and we cannot access it from our dev machine or from the public internet. Now, how do we make this accessible? Well, that's what we'll explore in the next section, right? So we have gone ahead and created the first pod. Then labels and selectors. This is a very important concept. So every API object, like a pod that we create in Kubernetes, will contain additional metadata. And this metadata is nothing but a set of key value pairs. And every object, basically a node in Kubernetes is an object, a pod is an object, a service is an object, a replica set is an object. So everything that you create in Kubernetes is an object. And every object is associated with a set of key value pairs, which are called labels. Now, as you can imagine, the abstraction that we are creating, for example, we have created a pod, and now we need to access that pod. So how do we access that? So before we can access that pod, we need to create what is called as a service. And a service is an abstraction of a logical set of pods identified by a policy, or it's defined by a policy. And the service is like a channel. It is opening up a communication pipe between one pod and the other pod, or the outside world and a pod, or a set of pods. So without a service, you can never reach the pod. So service acts as that intermediary. It is a thin layer that sits in between the caller of the pod and the pod. So it is not just sufficient if you have a pod exposing a port. You also need to go ahead and create a service that is responsible for opening up the communication channel. So when you create a service could be internal or external. And why is it important? For example, when I create a database pod, I don't want that to be available to the outside world. So I'll create a service that is very internal. So the web server pod can talk to the database pod through an internal service. But when I want to expose the web server pods, I want to create a different type of service that is available on the public internet. So essentially, the service is how you will interact with a set of pods. It is the window to pods. Without service, you can never ever reach a pod running within the cluster. Even internally, for example, if you have launched a database pod and you have launched a web server pod, they cannot talk to each other. You need to create a service which will act as that intermediary connecting the dots. And this intermediary can be an intermediary between two internal pods or an intermediary for the external world and the internal pods. So that's the reason why I say the service is responsible for communication, whether it is internal or external. So it acts, as I mentioned, as an intermediary. But how does a service definition discover what set of pods it needs to talk to? Well, that's where we have this concept of labels and selectors. So a service uses a selector, and a selector is like a filter that says, hey, Kubernetes master, give me access to all the pods whose label is web, whose label is name is equal to web. The moment that service is created, it can route the traffic to any of the pods that match the selector. So the selector is nothing but a query. It says, select all the pods that match the specific label, and any pod in your namespace, remember in this namespace that matches the label as defined by the selector will become available through the service. So the combination of labels and selectors establish some kind of a matching or service discovery. Officially it's called service discovery, and that's how you will end up exposing a set of pods either internally or externally. So a service has an internal port and an external port. So the internal port is available again within the cluster, and an external port is how you will talk to it from the outside world, either through a load balancer or either through a direct TCP IP connection. You can also create services using either TCP or UDP. So now let's go ahead and access our Nginx web pod by creating a service. So the next step in our session is to basically create a service and associate that with the pod we created in the last step, right? So let's go ahead and look at the definition of a service. So now we are looking at a service definition. We're targeting the API version v1. The kind of Kubernetes object we are creating is called service. It has metadata, very similar to the pod. It also has labels. But what is very important is it has a section called selector. And there we mentioned name is equal to web. And this single line associates the service with the pod because the pod also has this definition called name is equal to web. So one or more pods that match this label will be picked up through the selector. So this establishes the association or matchmaking between the service and the pods. We are defining the type of service as node port, and the node port is basically instructing Kubernetes that make it available on every node so that we can talk to this pod from the external world. So it is currently available on the droplets port. So if you hit that port on any of our worker nodes, you will automatically see the pod responding. The port that we are exposing this is 80, which means internally this is going to be made available on 80. It could be slightly different on the node port, and we are giving it a name. It's a best practice. And the target port on the pod is 80. For example, for some reason, your application is listening on port 8080 in the pod, then your target port will also be 8080 because that's how the routing takes place. But in our case, both the target port and the port are 80. So we'll leave that as it is. That's about it. All this does is open up a channel so that we can talk to every pod that matches this criteria, which is name is equal to web. Pretty straightforward, right? And now let's first check if we have any services. So kubectl get services. There is one internal service called Kubernetes, and it is cluster IP. Now, if you're wondering what is cluster IP, well, if you're creating an internal only service, it is going to be of type cluster IP. But in our case, we want it to be available on the external network. So we are now creating a node port. So as usual, I'll use kubectl create with -f, and we'll go ahead and create the simple service.yaml file. We'll feed that, and now the service is created. So let's come back and repeat get services. So now you'll actually notice that there is a web service and it is listening or it is created as a node port type. And here you'll notice that internally it is available on 80, but externally this is the port. So let's keep this here. But how do I basically access? You know, even now I'm not sure how I'm going to end up hitting my Nginx web server. For that, all we got to do is grab the IP address of one of the worker nodes. I love this nifty mechanism of copying the address just by clicking on this. Then we'll come back and do a curl and grab this port, put it here. There we go. This is Nginx. And if you really want to see the output in the browser, grab this, open it up in your favorite browser, and there we go. This is Nginx. So what we have done is we created a pod, and then we created a service to expose that. And how does the service know which pod to talk to? Well, the combination of labels and selectors make that happen. Perfect. So if you understand this, you know a significant chunk of Kubernetes, because a lot of beginners don't understand this. And even when I was learning Kubernetes a few years ago, I kind of struggled to understand how this matchmaking happens and how we can expose the pods. But understanding this is very, very critical to make progress. And I hope I made this concept simple for you to visualize and understand. Excellent. So what we have achieved in the previous step was exposing pods through services. Now, let's spend a minute visualizing this. So what happens is, in Kubernetes, you don't end up creating just one pod. It is not a good idea. Even when you're running VMs in production, it's not a good idea to have just one virtual machine running your web server. And containers being so lightweight and they can be scaled so rapidly, there is no reason why you should be running only one container or one pod. So what we'll actually end up doing is we'll run multiple pods, and they'll be placed on any of the available nodes. There is no hard and fast rule that Kubernetes has to place your pod on only this node until you explicitly specify. There is a concept called node affinity where you can force Kubernetes to position your pod on a specific node. For example, you are launching a database pod, and one of the nodes has an SSD drive. So you want to make sure that your database pod is always mounted to that node with SSD. So you can request the master to say, take this database pod and place it on this node every time. So that is actually called as node affinity. But if you don't mention the node affinity, Kubernetes will make the call and will schedule your pod in any of the available nodes. Let's say we are running 4 different pods, and they are called red. There are 3 instances of red nodes, red pods. Then we are running 1, 2, 3 green pods, and then we have exactly 3 yellow pods, right? So we created all of them, and we named them, or rather we gave metadata as color is equal to red, color is equal to blue, green, and yellow. So that is the label that we gave to this pod. And then when we are creating a service, I want S1 to route the traffic to all the red pods. So there, I basically create a selector, and in the selector definition, in the selector section, I mention that color is equal to red. and that's it. Now, any request that comes to S1 will automatically get routed to one of the red pods running in any node. It doesn't matter which node it is. It can automatically get routed. And there is also no specific mechanism on how a service routes the traffic. For example, let's call red 1, red 2, red 3 as R1, R2, and R3, right? Now, when you hit S1, you never know whether it is going to be R1, R2, or R3, which is going to be responding to your request. It is completely arbitrary, and Kubernetes will route the traffic to one of the pods that match the criteria. Same thing with S2, S3, and S4, right? The only definition here is you define a service and mention selector, color is green, color is yellow, color is blue. And you can also play around with it. For example, if I take S4 and there if I put color is red, it will now start talking to any pod that raises its hand when it says, hey, who has color is equal to red as label. Now any pod that raises its hand will receive the request, one of the pods. So you can play around. Unfortunately, I don't have a lot of time to cover the concepts of services in depth, but I hope you get an idea. So this will give you a good understanding of how services discover the backend pods. Excellent. But again, as I mentioned earlier, you would never run just one pod. It's not a good idea. So one of the advantages of running containers is you can scale them pretty rapidly. Unlike virtual machines, which are heavy, takes minutes to come up and register with a load balancer, pods can be very quickly launched. If I have to run more pods, do I need to create multiple pod definitions in a YAML file and keep creating them through kubectl or submit them to the master API server? Not exactly. If you know how many copies of pods you need to run at any given point of time, you can define them as what is called as a replica set. A replica set ensures that a pod or homogeneous set of pods are always up and running. So if you say, here is my web server pod, and at any given point of time, I want to run 3 copies of it, 3 instances of it. And when you're defining it, you're essentially creating what is called as a replica set. And a replica set will always maintain desired number of pods. Later on, for some reason, one of the web server pods gets killed, due to some hardware issue or due to some buffer overflow, it could be anything. So one of the pod gets killed, and because it's a part of replica set and replica set is constantly monitored by the controller, it immediately brings up another pod to match the count of 3. So it always maintains the desired number, desired count, even if a node dies or even if a pod dies. The only condition is if the cluster dies, then it can't do anything. But as long as the cluster is alive, it will honor the definition of a replica set. Similarly, if there are excess pods which go beyond the number of pods defined in the declaration, they get killed, because the job of replica set is not to go above or not to go below the desired count. It always maintains those many number of pods as defined in the replica set declaration. So new pods are automatically launched. They get deleted, or when they get deleted or terminated, new pods automatically show up. So creating a replica set with a count of 1 ensures that a pod is always available. So like a mythological character, every time you kill a pod, another pod shows up. So it is impossible to delete a pod which is a part of a replica set. So you can basically define your replica set with count of 1 to make sure that even if a pod dies, it immediately shows up, because someone is monitoring what is the available count, what is the desired count, and they're ensuring that it is matching. And who is monitoring and who is ensuring all of this? It is the Kubernetes master. Actually, the controller component of master monitors the replica set, all the replica sets that are running, and ensures that the baseline configuration is always maintained. So that is the beauty of replica set. And replica sets are also associated with labels and selectors. So when you're defining a replica set, you will have label, and every pod will automatically inherit those labels so that they become discoverable by a service. All right, so let's now go ahead and scale our Nginx through a replica set. So now we are running a pod. So kubectl get pods will show us it's running. You can delete this with kubectl delete pod web pod. Okay, so let's go ahead and get rid of it, because now we want to launch the same pod but as a replica set. So now we have 0 pods running. So let's take a look at the replica set. So replica set, the API version I'm targeting is slightly different, but don't bother too much about this. This is moving pretty fast, and just make sure you are using the appropriate API version. You can refer to the documentation and get the most current API version depending on the cluster version that you're running. In my case, I'm running the most recent one, which is 1.9 point something. If you actually look at this, I'm running 1.9.2. This is almost like cutting edge, and this requires that I use this specific API version, but otherwise you can pretty much keep this as V1 if you're running the more stable older versions of Kubernetes. So kind is replica set. It's not a pod. Here it is pod. Here we are defining it as a replica set. Metadata, we are giving it a name WebRS, and here we had web pod. And then we have same set of labels. Name is web, environment is dev. And within spec, we are defining replicas as 3. This is the most important part of a replica set. What this tells Kubernetes is to make sure that at any given point of time, we have at least 3 pods running as a part of the replica set. We're also defining, what are the labels that the replica set should monitor. So we are saying match labels, name is web. So even if there are other pods that match this label, the Kubernetes controller would kill them, because the only condition for running this is any pod should match this. That means if we have launched a pod and the current count is 1, then we come back and launch this as 3, because they share the same metadata. Kubernetes controller will kill one of the pods to make sure that the pods that match these labels are always 3. So it doesn't matter even if it is created outside of a replica set. What is more important is this. So if you want to make sure that your replica set is not interfering with existing pods, give a unique label, right? So that's the idea. Now, since we have deleted the existing pod, it shouldn't really matter, but it's normally a good idea to have a different label so that your pods that are standalone pods outside of replica set are not conflicting with the pods that are created through the replica set. The naming convention is taken care, but the metadata that you give got to be slightly differentiated. All right, so now we have the spec. The spec part is exactly like the pod. In fact, it is a copy and paste. So if you have more than one container, that can pretty much go into a replica set, because if pod is a collection of containers, a replica set is a collection of pods. It is another layer that encapsulates a set of pods, and all of them are treated like one replica set. That's it. That's all you need to know about replica set at this point. So let me go ahead and create my simple RS. Okay, now the replica set is created. How do we get this? So kubectl get replica set, name is WebRS, desired count is 3, right? This is the desired count. This is current, and the age is 9 seconds. So now you can verify this with kubectl get pods. And now you'll actually notice that, now you'll notice that there are 3 pods, and WebRS is the replica set name, and anything that follows after that is a random arbitrary name to avoid any conflicts. So now we have 3 pods. Does our application still respond? Absolutely, because they all have exactly the same pod running. So even though we killed the original pod that we created as a standalone one, even though we deleted that, these pods still match the definition of our service. So this web SVC is still able to route the traffic to one of the pods that belong to the replica set. All right, so let's do some funny thing, right? So what I'm now going to do is I'm going to run this in watch mode. Okay, so in my terminal window, which is here, oops, I should have exported. Okay, I need to export this, and now it should work. Okay, so now you'll notice that we are watching the count of pods, and currently there are only 3 pods. So I'll grab the very first one, and I'll go ahead and manually delete it. So let's delete this pod. Okay, and keep an eye on this. Excellent. So now what happens is this pod is getting terminated, and as soon as that is getting terminated, you will notice another pod getting created. And in just a few seconds, in less than 30 seconds, we should have another pod showing up. And that is how a replication controller, a replica set, ensures that the desired count is maintained. You can also go ahead and kill any of the pods, and it shows up again. That's the beauty of packaging your pods as a replica set. In fact, once you appreciate the power of replica set, you will never use a pod as a standalone pod. You'll always package that as a replica set, unless you have very specific reasons, like you're running a stateful pod and you don't have the luxury of deleting a pod and recreating it, unless you're running what is called a stateful set, which is the last session of this series. So stay tuned for that. But at this point, you can go ahead and safely delete any pod, and it still shows up as a part of the container, as a part of the replica set. I'm sorry. So excellent. Now we have looked at all the core primitives. There is one last thing that I want to show you, which is called as a deployment. A deployment is like a more convenient mechanism to manage the application lifecycle. If you are familiar with platform as a service offerings like Cloud Foundry, IngeneYard, Heroku, any of these PaaS offerings, you appreciate the ease by which you can deploy applications, right? For example, you push a new version of the application and without any downtime, it automatically starts performing an upgrade. Some instances of your application are running V1, some instances are running V2, and gradually the traffic gets moved to V2 and everything gets stabilized. So those are called rolling upgrades. Similarly, there are occasions where you need to do what is called as blue-green deployments. A blue-green deployment is a very controlled mechanism of performing upgrades. For example, you have rolled out V2 and you want to monitor carefully before you upgrade, or rather replace V1 with V2. So what you will do is you will first deploy 25% of the instances with V2, and 75% are running in V1, and you'll closely monitor how your V2 is responding through logs and user feedback and so on. And once you get confidence, you'll basically move 25% of your V2 to 50%. And again, you'll constantly closely monitor that. And once the confidence level goes up, you will turn V2 to 75 and eventually to 100%. And at this point, V1 is completely out and you're running it on the latest version. That is the advantage of using a deployment, more like a PaaS like offering or PaaS like capability. So it is nothing but a combination of pods and replica sets in one declaration unit. And it just gives you a lot of convenience when you're performing continuous integration and continuous deployment. If you're not using that, you may not find a lot of advantages of using deployments, but in production, it is always recommended that you package your application and roll it out as a deployment, because it gives you a variety of benefits in maintaining the application. So I also want to walk you through how you deal with deployments, not very different from what we have seen so far. So here, this is an deployment. So it looks exactly like a replica set. In fact, if you compare and contrast, you'll not find a lot of differences. The only thing is, let's say if you rolled out a replica set, and currently this is running V1 of your application, and how do you upgrade? You want to delete your current replica set and launch another replica set with V2, but there's going to be downtime, because you're upgrading one image from V1 to another image, which is V2. But if you are packaging the same application as a deployment, and when you roll this out, the best thing of using a deployment is you'll never have to delete an existing deployment. You can perform an in-place rolling upgrade. That is the biggest advantage of using a deployment. So let's go ahead and try this out. We don't need this, and I'll turn this into full screen. All right. So let me, oh, by the way, let's actually go ahead and scale our replica set, right? That is the fun part. So here we have, let me go back and put this in watch mode. So we have 3. How about scaling our replica set? So it's very simple. kubectl scale replica set / webrs, which is our replica set. And how many replicas do you want? Well, I want to replicate 10, right? So just hit enter. And now you'll notice that as soon as this request is sent to Kubernetes, you'll notice 10 such pods are being created. And in just a few seconds, you will see all of them moving to a running mode. That means with just one command and less than 30 seconds, you scaled up your application from 3 containers to 10. And that is going to be super fast. This is one of the biggest advantages of using Kubernetes. And of course, the replica set, because you're not dealing with one pod, you're basically dealing with a unit, and you can scale in and scale out that unit at runtime. So 35 seconds, there we go. We have 10 pods running as a part of the replica set, and all of them are now serving the traffic, which means if you have a large cluster with multiple nodes, you will instantly scale your application with no bottleneck. If you want, you can also bring this down to just 2. Now, when we actually say scale replicas to 2, now you'll actually notice that all of them are getting terminated, and in just a few seconds, it will be reduced to just 2 pods. And this is a great advantage of using Kubernetes. Excellent. So now that we are familiar with a replica set, let's move to deployment. But before that, I'll go ahead and delete my replica set, which is webrs. And once this is deleted, all the pods that are associated with this replica set will also get killed. So now there are no pods. So let's now create a deployment. So again, I'll call this with simple deployment.yaml. And how do you verify this? kubectl get deployments will show us there is one deployment called webdep. Desired count is 3. Currently 3. Current is 0 because it is still creating. And in there we go. In just a few seconds, it'll move to a count of 3, both desired and current. And you can actually check the number of pods. So now you'll notice that web-dep is the prefix, because this will identify the deployment. And then there is an arbitrary number followed by a pod name. So this is how you create a deployment. And once you have a deployment, you can very easily upgrade your pods to run a different version of container image, and you can perform what is called as a rolling upgrade. So that's about the core primitives. We covered a lot of ground. To summarize, cluster, it's a pool of compute, storage, and network resources associated with an underlying set of host machines, which are called nodes. So a set of nodes will form the cluster, and a cluster is how you will consume compute, storage, and network. Namespaces are the logical partitions of a cluster. Pods are the units of deployment. That's how you package and deploy your apps or containers. Labels are the key value pairs for identification and service discovery. Then we have services, which are basically the channels for us to communicate with a set of pods that belong to the same application, or technically that match the selector. Replica set ensures high availability and scalability of your application. You can easily scale in and scale out. We have gone from 3 to 10, and then we have gone down to 2. That is the scalability part. Deployment manages the application life cycle, so you can perform rolling upgrades. In terms of the commands, like every time I highlight the key commands that you need to learn. So kubectl create is how you will create a resource or an object in Kubernetes. To verify the creation, you will use kubectl get. And then to dig deeper into an object, you can always use kubectl describe followed by the object, which is object type, which is a pod or a replica set or a service. And then you'll give the name of the actual object. Kubectl scale, as we have seen, is meant for scaling a class of objects like replica set, replication controller, deployment, and so on. It cannot be used with everything. And finally, to clean up resources, you will use kubectl delete. So kubectl delete takes the object name or the file and deletes everything that is declared in that file. So those are the key Kubernetes commands to explore. And like every time, this entire demo has been turned into a tutorial, and it is going to be published on the landing page very soon as a DigitalOcean community tutorial. And you will be able to copy and paste and run all these commands to basically have the same steps repeated in your dev machine. So that brings us to the end of this session.